Thank you for inviting me for the nice workshop. Today my talk is about the domain observation technique by using a Kerr microscope for the permanent magnet, especially a neodymium ion ball magnet. Firstly, I'll talk about the background of the magnetic domain observation of neodymium ion ball magnet. Second, I'll talk observation results of magnetic domains in high magnetic field and elevated temperatures. Finally, I'll talk about the relation between magnetic domains and microstructure. Okay, as you know, high coercivity neodymium ion ball magnets are required with a small amount of dysprosium for electrical vehicles applications. To increase coercivity of the neodymium ion ball magnet with a reduced amount of dysprosium, many researchers have been investigated. Many studies have been investigated. One of the important techniques to enhance the coercivity is dysprosium grain boundary diffusion. In this paper, Nakamura, Shin-Et's chemical groups reported that the coercivity can enhance by this technique, like this figure, by using a dysprosium or a terbium. This figure shows the dysprosium compositional profile. Dysprosium exists only grain boundary phase. So, by this technique, the high coercivity magnet can be realized with a small amount of dysprosium. The bottom case is eutectic alloys boundary diffusion technique. In this paper, Nimus group reported the coercivity enhancement technique by using this technique. And in this paper, neodymium copper eutectic alloys used for high coercivity magnet. They investigated the microstructure of this magnet. So the microstructure of the magnet is very important to enhance the high coercivity, to enhance the coercivity of the neodymium ion ball magnet. Recently, gallium-doped neodymium-rich neodymium ion ball magnet produced by the Showa Denko Corporation has been investigated. In this paper, by this technique, the very high coercivity can be realized by using this magnet. And they, at the Nimbus group, investigated the microstructure of this magnet. In this paper, neodymium 6 ion gallium 14 phase can suppress exchange coupling of the 214 phase. So the microstructure and the magnetization process is very important to enhance the coercivity. So this figure shows the magnetization process and the domain structure change of this magnet. So coercivity enhancement techniques can suppress the propagation of the reversal domain. In this case, if the grain boundary phase is not so good, firstly, the reversal domain nucleate, and the reversal domain grew and propagate to the neighbor grains beyond the grain boundary, like this figure. In this case, the propagation of the reversal domain easily occurs, and the coercivity is very small. And in this case, the grain boundary phase is optimum. So, so the reversal domain nucleated. After that, the magnetization reversal suppressed at the grain boundary phase. So, to enhance the coercivity of the neodymium ion ball magnet, the role of the grain boundary phase during the magnetic reversal process has to be clarified. So, domain observation is very important to obtain the high coercivity magnet. Domain observation of the neodymium ion ball magnet has been investigated by many researchers. So this is one example of the domain observation result of the neodymium ion ball magnet by using the transmission electron microscope. The NIMS group reported the domain wall, observed the domain wall like this figure, and wall motion can be observed during the demagnetization process. The right side one case is eutectic alloys diffusion into magnet. So in this case, the wall motion hardly occurred. So and this technique is by using the transmission electron microscope. So in this case, they can observe the microstructure and domain structure at the same observation spot. This is very useful to investigate the mechanism of the coercivity of this magnet. The second example by Dr. Ono, by using the scanning transmission X-ray microscope. By this technique, a very clear and beautiful domain image can be obtained. And moreover, the chemical composition can be obtained at same observation spot. This figure shows the neodymium chemical composition and the iron chemical composition. So by using this technique, we can obtain the magnetic domain structure and the chemical composition. That is very useful to investigate the coercivity mechanism. The MFM is also used to observe the magnetic domain structure of the permanent magnet. Professor Kobayashi reported the domain structure and the demagnetization process of the neodymium ion boron sintered magnet. They reported the magnetization process, the surface and the inside, and they investigate the inside the magnet. The advantage of the MFM is resolution, high resolution, the nanometer size. So by using MFM, we can detect the nanometer size domain structure. So for example, hot deformed magnet or ATDR magnet has a very small size grains, about 300 to 500 nanometer. So MFM is very useful tool to observe the small size fine grains magnet. Okay, and in this figure shows the domain observation result by using spin polarized scanning electron microscope. Dr. Kohashi reported the domain observation result of the neodymium ion boron magnet. In this paper, the spin polarized SEM image was taken as the surface of the sample, and the surface was ion milled in the vacuum chamber. And they observed the domain structure change depending on the etching time. And they measured the spin polarization at this point and this point. So magnetization in the grain boundary phase and 214 phase was obtained in this paper. That's a very useful tool to domain observation for the permanent magnet. And my observation method is a Kerr microscope. Kerr microscope is a magnet optical effect by using the interaction between the polarized light and the magnetization. Kerr microscope spatial resolution is not so good, about a few hundred nanometers. But advantage of the Kerr microscope are for example, high-speed observation and simple observation systems. These advantages produce the useful domain observation method in a high magnetic field and at elevated temperature. So this Kerr microscope is useful to investigate the magnetization process of the high porosity magnet. Okay, I'll show you the, some observation example by using our Kerr microscope. In this case, we have observed the thin film. This figure is amorphous cobalt niobium zirconium thin film fabricated by the 5 micron wide rectangular pattern. 5 micron. In this case, 20 micron wide rectangular pattern. Okay, I'll show you the movie of the domain change during the magnetic field. In this case, the easy axis is this along this direction, and the magnetic field to the along the hard axis direction, and the magnetic field was swept positive field direction to negative direction. You can see the striped domain pattern and domain wall motion and the domain wall motion and the magnetization rotation. In this figure, dark contrast and bright contrast can be seen. Dark contrast and bright contrast shows the upward and downward magnetization component. So the wall motion occur and the magnetization rotation occur. If the magnetization tilt to the this direction, we can see the gray contrast. And in this case, it's 20 micron wide samples. Wall motion and the magnetization rotation is also occurred, and but you can see the triangular, the closure domain during the magnetization process. Okay. This is the triangular closure magnetic domain. The closure domain, the influence of the closure domain is different between the two cases. Influence of the closure domain increases at narrow width pattern. And second example is also thin film sample. This is amorphous thin film, and this is granular thin film. Firstly, the dark contrast can be seen, and you can see the nucleation of the reversal domain, and the wall motion and growth of the reversal domain occurred. And in the case of the granular film, the shape of the reversal domain is different, like this. Reversal domain shape is a triangle in the case of the amorphous film, but granular film case, very narrow line-shaped reversal domain can be seen. Okay, third example is a grain-oriented silicon iron electrical sheet for transformer application. You can see the stripe pattern, and when the field applied, very clear 100 domain wall moved like this figure. And right side one is a scratched sheet. You can see the 20 to 30 micron size scratch at this point. And you can see the domain wall pinning can be seen. So once more. Wall motion occurred, but wall pinning occurred at this point. So the domain wall like this figure. That is very interesting. So you can see the clear domain image by using our Kerr microscope. So Kerr microscopes are useful for the in situ observation of magnetization process in high magnetic field and elevated temperature. So purpose of this work is a domain observation of for neodymium ion boron magnet in high field up to 20 kilo L state and high temperature up to 150 degrees C. Okay, I'd like to show you our observation system, like this figure. And this figure is the optical setting of our Kerr microscope. Xenon mercury lamp is used as a light source, ultraviolet light source, and you can see the optical component, lens, and polarizer, and analyzer. And we use a high-sensitive camera, ICCD camera. So we can use ultraviolet light as a light source. High-resolution observation is possible by using ultraviolet light. And we set this microscope inside an electromagnet. The large electromagnet can apply up to 20 kilo L state. So we can observe the magnetization process of the neodymium ion boron magnet up to 20 kilo L state. This figure shows the resolution limit of the optical Kerr microscope. Resolution limit resolution limit is shown by this equation named by the Rayleigh limit. The wavelength of the light and the numerical aperture of the objective lens decide the resolution limit. So by this equation, short wavelengths produce the high resolution. This figure shows the dependence of the resolution limit on the wavelengths. You can see the 100 nanometer, about 100 nanometer resolution can be obtained by using the ultraviolet light. Wavelength is 248 nanometers. And this figure shows the optical photograph, the line pattern by using the commercially available ultraviolet light microscope. In this case, 80 nanometer resolution can be obtained by using commercially available microscope. This is not so Kerr image, but by using the ultraviolet light, a very high resolution can be obtained. So about 100 nanometer resolution can be obtained. So this is an observation result by using ultraviolet light. In our observation, we observe the magnetic domain of the neodymium ion boron meltospan ribbon. Meltospan ribbon has a very small sized grains. So we can see the very small size domain pattern. This is 1 micron scale. So you can see the sub-micron domain pattern can be seen by using this UV microscope system. And in this figure shows the observation result, observation example of the HDR neodymium ion boron magnet. In this case, this area, the contrast changed from the dark contrast to bright contrast. This area is about 300 to 5 nanometer. This data shows only one grain in only one grain magnetization reversal in this case. So the UV Kerr microscope allows observation of small domain patterns of the few hundred nanometer in size. Okay. And I show you the sample for the domain observation. This is a neodymium ion boron sintered magnet for vertical motor of the hard disk drive. The sample firstly cut to this shape and size, and we polished observation surface. The sample was polished to observe the magnetic domain. And after polishing, SiO and tantalum thin film were deposited for anti-reflection and antioxidant coating. So in this figure, this direction is easy axis of the magnet, and the magnetic field is also applied along the easy axis direction. Okay, I'd like to show you the movie of the domain observation result. In this case, the magnet was applied plus 20 kilo Lstat to minus 20 kilo Lstat. And we capture the domain image, domain movie, in this case from plus 4 kilo Lstat to 0. Firstly, almost grains shows a bright contrast. That means magnetized state, firstly. And when the magnetic field changed, you can see the dark contrast in the grains. So that data shows magnetization reversal occurred. Reversal domain nucleate around the grain boundary. And magnetization reversal propagated to neighbor grains beyond the grain boundaries. And you can see the large change of the domain contrast of around this area. And next, the observation result was image processed by using photo editing application. This is the observation result, the same result. And firstly, magnetized state, and when the field is 3.3 kilo Lstat, we can see the reversal domain. The darker contrast can be seen inside in this grain. Okay, and the contrast colored by blue color. Okay, and you can see the magnetization reversal occurred at this point. Okay, this photo editing, image processing is also has been done every 0.5 kilo Lstat, like this figure. So you can see the magnetization reversal at this point, and the reversal propagate to the next neighbor grains like this along this direction. And you can see the simultaneous magnetization reversal occurred at this area about over 10 grains. Okay, the broken line shows the grain boundary of this magnet. So you can see the simultaneous magnetization beyond the grain boundaries, and the propagation along the easy axis direction can be seen. So by this figure, reversal propagate beyond the grain boundaries, and so pinning force at the grain boundary is very important for high coercivity magnet by observation result by using Kerr microscope. Okay, next I show you the the domain observation at elevated temperature. This figure shows the domain observation system. Kerr microscope was set inside the large electromagnet. In this case, we can apply up to 16 kilo Lstat. And this figure shows the temperature control stage, like this photograph. The temperature control stage can control increase the temperature up to 330 degrees C. And to avoid the thermal damage to the lens from the heating sample, we used the objective lens with a long working distance. Working distance is about at 4 millimeters. By using this system, we have observed the magnetic domain structure. Room temperature 60 degrees C and 150 degrees C. You can see the magnetization reversal occurred like this colored area. Simultaneous magnetization reversal occurred at room temperature and at elevated temperature. But magnetic field occurring the magnetization reversal is changed. At room temperature, magnetization reversal started at minus 1 kilo-electron, but 60 degrees C at 0 to minus 0.5 kilo-electron, magnetization reversal firstly occurred. And 150 degrees C, magnetization reversal occurred at plus 1.5 kilo-electron. So we can see the decrease in the coercivity at elevated temperature. So, and simultaneous reversal area increased with increasing temperature. We can obtain the interesting data. So, magnetic domain observation can be investigated the thermal stability of the neodymium ion boron magnet. So next, we can observe the magnetic domain structure, but it is important where magnetization reversal occurred. So this figure shows the microstructure of the magnet. So relation between the microstructure and the domain structure is very important. So we observe the microstructure of the magnet at the same point by of the magnet by using the scanning electron microscope. Sample is a neodymium ion boron melt span ribbon. Melt span ribbon was fabricated by this figure. In this case, where speed is very low, low quenching rate produces the enlarged grain and low coercivity. So in this case, we observed the magnetic domain structure and the microstructure of this sample. This figure shows the same image of the melt span ribbon, neodymium ion boron, and in this case, titanium added 5% of the iron. So you can see the enlarged grain at this area. So enlarged grain were observed at the excess titanium addition. This is elemental map around this area. You can see the poor titanium distribution around the enlarged grain. Okay, and we observe the magnetic domain structure. Firstly, the magnetic field plus 14 kilo-electron, and magnetic field changed to plus 9.5 kilo-electron. The bright line-shaped reversal domain nucleated at this point inside the enlarged grains. Okay, this is a reversal area at 9.5 kilo-electron. And this colored area is a titanium enriched point. So we can investigate the magnetic domain structure and nucleation of the reversal domain and the titanium enriched point. So you can see the magnetization reversal occurred at the titanium enriched point. So excess titanium addition produced the titanium enriched point inside the grain. Very poor titanium distribution, and so the poor distribution produce the poor hard magnetic properties. That is because of the nucleation of the reversal domain from the titanium enriched point. So this is reason of the decrease in the coercivity in this sample. Okay, I summarize my talk. Kerr microscope having a high resolution and in situ observation up to 20 kilo-Elstet and 150 degrees C was developed. Relation between the microstructure and the domain structure was established to evaluate the effect of the addition of titanium on the magnetic properties of the neodymium ion monomer spun ribbon. Reversal domain nucleate at the titanium enriched point inside the grain. The excessive titanium addition promotes poor distribution of titanium and causes low coercivity. Thank you for your attention.